Columns are members, and this is going to be the review type assignment from undergrad. But columns are members that are predominantly see only axial load. That's not totally true. We can see beam columns that receive axial load and moment, but we're going to primarily be talking about columns that only see axial load. Columns fail by either crushing or buckling. Crushing happens to short and squatty members, or we would say something like the slenderness ratio, K over R. Remember slenderness ratio? Heard of that before? K, L, and R. What's K? Yeah, effective length coefficient, something like that, right? Takes into account what your boundary conditions are, right? For a pin-pin column that's non-sway, it's 1. L is the length between your supports, and R is your radius gyration with respect to the axis of buckling. I'll say this again for those that haven't had me or if it's been a while. There's not always, you have to understand and think about in which direction the column is buckling, and that is the R that you'll use. It's Rx or Ry. If it's buckling about the x-axis, it's R sub x. About the y-axis, it's R sub y. But that crushing happens when K over R is extremely low. Crush strength is equal, and equal is a bad word, close to the yield strength of the material. Buckling happens when members are long and slender. It's when K over R is high. What's high? Oh, we'll come to that. And it's when our member would rather deflect to the side than stay straight. It would rather move to the side in a deflected pattern. It just moves and stops than stay straight. And we're going to say the Euler buckling equation, this critical equation that we're going to be talking about in this class, right, that describes this, is sigma critical is pi squared E over KL over R squared. Because of imperfections, though, this equation only controls if K over R is extremely large. Okay, and we'll talk more about that coming up. Notice that the buckling capacity of a column has nothing. It's just fun to say that in funny ways, but absolutely nothing to do with the strength of the material. K over R, pi squared E over K over R squared. There's no Fy in there. There's no Fu. There's none of that. It's because the buckling capacity of a member, and we're talking about buckling capacity, only depends on stiffness, geometry, and imperfections. Stiffness, geometry, imperfections. Theoretically, buckling actually should not happen. If you talk about mathematically, pure mathematically, you start to load a member up and you put loads in the center of it. What's the stress? It's P over A, right? It's P over A forever, right? Well, what happens is that there's a thing called imperfections. Either imperfection in the length, an imperfection in the loading, an imperfection in the material, and the thing starts to bend a little bit. Starts to be a little bit of moment that develops. Okay? A little internal bending that happens. When that starts to happen, the member would not like to stay straight anymore. It would like to deflect to the sides. Awesome. Theoretically, buckling should not happen. However, due to imperfections of the member, initial curvature, unequal stress distribution, unequal loading of the column, it would rather buckle than crush. Flip this over on the back page. So if we draw a free body diagram, I'll tell you, I didn't quite get buckling for the longest time, but when I started to think of it in this terms, this is when it made sense to me. Actually, I took one whole class called stability in graduate school, and it was all about buckling and lateral torsional buckling. Column buckling and lateral torsional buckling. And then there's also other kinds of buckling we don't talk about, like torsional buckling. So instead of things kicking to the side, they just spin. It's weird. The only cross section that does that, though, is a cross. So if you make any Jesus columns, watch out. Like, that's how they fail. They actually fail in torsional buckling. Yeah, they spin. They just spin. And there's lateral torsional buckling. We talked about torsional buckling. We talked about column buckling. That's about all we did. But don't worry, I've taken all the goodness out of that class and tried to distill it down into what's important and left all the differential equations behind. Oh, you're welcome. Okay? Or the majority of the differential equations behind. So what's going to happen is when you start to load this member up, that's what I just talked about in the previous page, it's going to want to buckle to the side, and it just so happens that there's this internal restraining moment. This restraining moment caused by the material. And if this internal restraining moment is large enough, it's higher than what your actual buckling moment is, your kind of external moment that's created by this load at eccentricity. You're good. You're safe. When you unload it, it'll just go back. It'll go back to where it was. It'll just move backwards. Okay? And when you get to this point where this internal restraining moment happens to be equal to this external moment, and that is right at the buckling load. That is if you have a human or somebody that blows, a gust of wind that blows on the column, it will break. If you add another feather to the top of the column, it will break. This is a mythical place that we don't ever get to and never want to be close to, but it's what's supposed to happen. And then there's this point when your external moment is above this internal moment, and this thing goes forever. It just moves and moves and moves, and that's bad. In civil engineering, when things move, it's bad. They move a lot. Continually move. Does that make sense? Awesome. Now, in undergraduate class, I like to do these things, and if I had more time, I would do it in this class as well, but I want to cover more material. If you have we had a can, I do this thing where I take these pop cans and I stand on top of them. And like, look, the pop cans hold me. How cool. And then we come up and we ding them. We hit them with a yardstick on the side, creating an imperfection. And once we create this imperfection, it creates an eccentricity, and boom, I collapse. And it's so funny to watch me fall down, right? Fall on my rear. Okay. So what happened was when I very first stood up there on top, this external moment was not larger than the internal moment, and we were all safe. The world was safe. But when some lucky student gets to tap the pop can from the side, creating an imperfection in the pop can, I fall. Another thing, sometimes if I find a pop can that just naturally has already been crinked and come back, there'll be a little bit of imperfection on it. You should try it for yourself. If you don't believe me, do it for yourself. Dan, you may need 2 pop cans per foot, okay? But you can do it as well, okay? You're a 2-canner. You stand up on top of this, and you put your feet on top. Better have chairs on both sides to hold you up, okay? And if there's an imperfection on it, it'll just collapse immediately. It won't be able to hold you up. Why? Because buckling depends on imperfections, stiffness, and geometry. Nothing to do with strength. You'd say, hey, this can wasn't any weaker. No, it wasn't. It just had an imperfection in it that was magnified. You with me? Awesome. This is something we call the P delta effect. Small imperfections are magnified under axial load, increasing this internal moment, and this is a big problem with load combinations. What I mean is this is a big problem in actual structures, and you have things like wind blowing and axial load going on. The good thing about that saves us, though, is it's rare that we're having a dance party on the roof during a tornado. Doesn't happen very often. Okay? So because of that, when our horizontal loads are high, our axial loads are usually not as high. Usually in buildings. Okay? If you have a structure that's almost entirely led by dead weight, like a bridge, okay, then your axial loads are going to be high when horizontal loads come in. The good thing about our columns are usually pretty skinny. They don't really pick up a lot of load, a lot of wind load. They're just too thin. The wind goes around them. What they do pick up is 18-wheeler impacts. Okay? If they can hit them, those truck drivers will hit them. Okay? And when they do, that can cause issues. So oftentimes for I can't speak for all states, but I can speak for the state of Texas, what actually controlled our design on columns with roadways underneath was an 18-wheeler impact, horizontal impact. Okay? Wasn't anything to do with gravity loads. All right? All right. And you put these things called bollards or whatever, or all kinds of things in front of them, they will find a way around them. All right? I'll never forget, I got a call once. I'd been at Tech Stop for 2 months, but I don't know how this ever happened. These two 18-wheelers was in Waco. Two 18-wheelers were going in opposite directions. One happened to be totally full of jet fuel. The other happened to be totally full of large trees. The one with the large trees ramps the median on I-35, sending the trees into the air, and where do they land? Into the 18-wheeler full of jet fuel. And where does this happen? All on a bridge. So engulfed in flames, fire everywhere. If anything bad can happen, it will happen on a bridge, okay? Crazy, crazy stuff happens under and on top of bridges, okay? And so that just goes to show you that it's hard. It's very, very hard to anticipate all the badness that can happen to your structures. Okay, now the cool thing about this P-delta effect, the cool thing about being out in the field and seeing something like this, I hope this never happens to you, but seeing like this something happens, the structures warns you. As it's getting loaded more and more and closer to its collapse load, it will magnify any imperfections that are there. So if you have something like in a 10-foot long member, a 1/8 inch imperfection, 1/8 inch imperfection, you would never see that if you look at a column like that's around us around the room. In 10 feet, you'd never notice if it's off by an inch. It's probably off by more than that right now, and you would never even realize it. But if that column starts to move such that you see an inch difference between the top and the middle, I bet you're going to start noticing it. Depends. Not everyone does. Or if they do, they don't think much of it. Wow, that column sure is getting curvy. That's when you run. Okay? You're welcome. I just saved your life. Worth every penny this class cost. Okay, great. That's what this column, that's what this does. That's what the P-delta effect does. Okay? It magnifies any imperfections. Okay? It also is if you have horizontal and simultaneously axial load, it'll magnify it. It's not that big of a deal. There's all kinds of ways to take it into account. What you really do is you have to do this iterative approach where you put some axial load on it, you put some horizontal load on it, more axial load on it, more horizontal load, and those things will magnify. Those things will add to one another. Okay? That's what you have to do. What we usually do is use a computer program like Reset, and you hit the little P-delta button, and it does the same thing. If one wanted to, in something like similar to like it should be covered in, I personally think it should be covered in something like classical methods of structural analysis or computer-aided design. You would do this by hand, okay, and figure out how this is done by hand. But not in this class. At least you know it exists, though. And you can always teach yourself, right? That's what you're learning how to do, is teach yourself stuff. Column behavior. Ideally, columns should either crush, that's a P over A type calculation, or buckle, is pi squared E over K over R squared. However, real behavior is a little different, and I show this graph over and over and over again. I love this graph. I want to marry this graph, but I'm already married, and my wife would probably get jealous, okay? But the cool thing about this graph is that it explains everything about column buckling. Everything. Every problem you work in this class when it comes to columns can be described by this graph. We have sigma critical up here. We have K over R down here. We have a flat portion. We have a nonlinear portion. What's the flat portion? Crushing. What's the nonlinear portion? You're buckling my heart. Oh, I've been saving that one for a while. Buckling. Buckling. And what was this? These dots, these random gunshot dots that are nowhere near the theoretical crushing or buckling. This is the test specimens. This is the test behavior, the actual behavior, I guess we could call it. The behavior of test specimens. I'm sorry, I didn't hurt you with all that knowledge I'm throwing on you. Ooh, I'm just bringing them all out today. So, we got this actual behavior, we got this crushing, this buckling. What? How can the actual behavior be different than the crushing or the buckling? Why? Imperfections. Yes, imperfections. That's right. Imperfections are the reason why there's a difference between these two columns. Imperfections. Residual stresses, non-perfect loading, non-straight members. These are all things that we call under the label imperfections. So, what are these things? What's the K equal to? The effective length factor. Yeah. The end restraint. End restraint factor is what we'll call it. What's that? Oh, it's on the next page. What's L? Length. Length of what? Your nose? The column. The length between supports, right? How about R?
Radius of gyration around your axis of bending.
That's right. Radius of gyration around axis of bending. What's pi? 3.14159808. It's pi. And what is E? Modulus. Is modulus still always constant? Theoretically. And KL is kind of like this equivalent length. Equivalent pin length. That means we're taking our structure and we're turning it into a pin member. That's what KL does for us. It is for us. End restraint factor. What is this all about? Now, we're going to cover this at lightning speed. You can go back and look at it for yourself. You should have seen it previously in your life. The very, 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 very first question you ask yourself whenever you're solving one of these problems is sway or no sway. And how you decide if it's sway or no sway is you ask yourself, can the ends of the member move with respect to one another? So in this column, whenever we draw a brace in this class, we assume the brace is infinitely stiff. Okay? And in this case, if we have an infinitely stiff brace here, then as we load it, it's not going to compress, so it's good. So the top will not move with respect to the bottom. And this one, an AIC actually requires brace design and forces brace design to meet these criteria. And I'll tell you, the rule of thumb for brace design, it's 1% of the axial load. 1% of the axial load in this column, that's what you assume is in the brace. Design a brace for that, and you are good. I'll prove it to you later. In this situation, when we draw the deflected shape, oh, what's that look like? If you can't draw deflected shapes in this class, you are going to be in big time trouble. That's the deflected shape. That's what it looks like. And you're going to say that's a sway. Why is it sway? Because the top moved with respect to the bottom, didn't it? Yeah? Yes. Great. Now, what happened was this great guy named Leonard Euler. Okay? And he derived the equation, the buckling equation. It didn't look like the one that we use in terms of stress. He did it in terms of P, in terms of load. Okay? But he basically derived an equation for a pin-pin column. And people were like, wow, that's cool. Let's derive the differential equations for all the other columns. And I have done these. Oh, thank God you don't have to. Okay? And you derive the differential equation for this, and you find the answer is actually 4 times. The capacity is 4 times. If you change the boundary conditions to be fixed at the top and fixed at the bottom, it's 4 times stronger. In this case, where it's a pin at the top and fixed at the bottom, it's actually 2 times stronger. You say, what is going on here? I see a pattern. Something's going on. What people started to do is they started to look at the deflected shapes. They say, you know what? That deflected shape happens, if I magnified it, it would be like, whoop, it's the same. They're the same. That 0.5 distance, that 0.5 L, if this is L, this is like having a little bitty 0.5 L pin-pin column in the middle of my fixed column. They're the same. And if they did this one with the pin fixed, and they found this distance, it's 0.7, it's actually root 2 over 2, okay? It's 0.707 and some change. They found that, hey, that's like that deflected shape happens to match exactly to a pin-pin column of length 0.7 L. Hey, I see a trend here. What they came up with is this K factor, this effective length factor, to say, hey, this has an effective length of 0.5 times L. This has an effective length of 0.7 times L. It's a trick. It's a way to go without solving lots of differential equations to go from geometry different than pin-pin to something that's an equivalent to a pin-pin. You with me? Oh, cool. Now, this is the table. This is the table that's in your steel manual. I just hate the form that it's in your steel manual. I don't like it. Okay? So I redrew it. That's what you do. When you don't like something, you just do it your own way. Right? That's right. And I broke this up. And I broke this up into sway columns. And I broke it up into non-sway columns. This is really cool and easy and fun and awesome. So here's our favorite pin-pin column. Here's our pin-fixed column, and we got 0.7. Here's our fixed column, we got 0.5. Here's a fixed sway column. So this one, you can still use the effective length, and it's effective length of 1. And why is it 1? Because if you draw the deflected shape, if I take the deflected shape on the top, and I flip it over twice, and put it down here on the bottom, oh my God, look at that. It's a pin-pin column of length L. And if I do the same thing with the flagpole problem, a fixed free problem, and I send this to the bottom, this is like a column with 2L deflected shape. And I don't have the room to do it up here, but we can imagine that this would also be a 2L. So the K is 2, the K is 2. This is review. Oh, that was awesome. And this is something that anyway, this is easy. You should know this. You should have seen this. And these are all cool and all, but actual structures don't look like that. Actual structures don't have a huge blocks on top of them. At least not usually. Maybe some wild art. I don't know, maybe the architects like to do stuff like this. Put a big old block on top of it. She's not answering. I respect that. Now, when it comes down to actual structures that humans or engineers like to make, they actually have all kinds of columns and beams coming in to the different sections. Okay? And we're going to find that these columns and beams come in here, and they're not pinned, and they're not fixed. There's something in the middle. There's something in the middle. They're a rotational spring is what we're going to do. And that's what a rotational spring is. It's a way to live somewhere in between the fixed and the pinned world. Okay? It's somewhere in the middle. And we talked about moment connections previously, right? We talked about how stiff they are and all that stuff. It's very similar to what we're doing here. Okay? Rotational spring. And we'll find out that their answers have to be anywhere between 0.5 and 1. They have to be anywhere between these two values. That's what they have to do, and that makes sense. We got fixed, versus pin, fixed versus pin. That bounds the problem. This is as stiff as you're ever going to get. This is not as stiff as you're ever going to get. Is the least amount of stiffness as you're going to get. As flexible as you're going to get with a non-sway system. Because what happens if I make one of these free? Unstable. Yeah? Yeah. Cool. So, the same thing happens over here with sway frames. The only difference is they move to the side. And what we're going to do is we're going to take whatever columns and beams come into this joint, and we're going to be like, and we're going to make a rotational spring. Okay? Just make that noise in your head every time. Okay? And you're going to say, boom. That's an equivalent rotational spring. That's what you do with something called the alignment chart. The alignment chart. The alignment chart is going to become our friend. Okay? It's going to be something we know and love. We're not going to get there quite yet. There's some example problems that I'm not going to cover. These are some equations that you can use to solve for the buckling capacity. There's also table 4.1. There's also table 4.22 in your steel manual. You should know how they work. The biggest one on 4.22 is easy. It's the one where you look up the KL over R and you have different FYs. Okay, great. Then there's table 4.1. That one you have to be really, really, really careful about. Because table 4.1 assumes the column is buckling about the least radius of gyration. Right? It assumes the column is buckling about the least radius of gyration. So there's table 4.22, there's table 4.1, and if I had my steel manual, I'd show them to you. But you all have steel manuals, and you can look at them. Be very, very careful before you use table 4.1 unless you really know how it works. Because if it's buckling about the strong radius of gyration, you need to divide by Rx over Ry. And if you don't remember what I'm talking about, look it up. It's in a book, I swear. Or talk to me about it, too. So I work an example problem here. The very first step is I got to find if it's sway or no sway, and the answer is no sway for this one. Solve for KL over R. I did that about my X and my Y. I find out which one's larger. Why does that matter? The larger KL over R controls. How do I know? Because it goes back to my chart that's my mistress, right? As the largest KL over R gets larger and larger, what happens to the capacity? It gets smaller and smaller and smaller, right? Right. So it controls. I've worked this problem 3 ways. You do not have to work it 3 ways. You only have to work it 1 way. But I just want to show you how it works. I've worked it with the equation. I've worked it with using table 4.1. And I've worked it with using table 4.22. And the answers are all really, really, really close. Cool. Hey, there's another example problem. Hey, more example problems. The bottom of the page here. And those are one of the things you're supposed to read on your own. The bottom of the page here, I say, what would happen if we removed a brace and instead used a moment connection? So if I take the brace and I used moment and moment up here, would it fail? No, it would not. In this direction, would we say it's sway or no sway? No sway, but it actually depends on the diaphragm, right? It actually depends if it's a rigid diaphragm or a flexible diaphragm. Rigid diaphragms are what? Concrete. And also steel Roofs with cross braces. Has to have a cross brace in the diaphragm. Or concrete. What's a flexible diaphragm? Timber. Flooring system. Steel diaphragm, no cross brace. What's the difference? If it's a rigid diaphragm, we assume that whatever this frame does, this frame is going to do as well. They're together. They're linked together by the rigid diaphragm. If it's a flexible diaphragm, every frame for themselves. This could not work under a flexible diaphragm. The back frame has a pin system. It's going to try to fall over. It's going to ask for help. If the diaphragm's not strong enough to transfer the shear, or stiff enough to transfer the shear to ask for help, fall right over. Does that make sense? Okay. This direction. What is it? Sway or no sway? Sway. How do you know? The top can move with respect to the bottom. If you don't ask yourself that every time, you will get every problem wrong. Every single one will be wrong. Sway, no sway, boom, boom, boom. Great. How do we solve this? Come on, past Steelies. Who's had my class before? How do you solve this problem? What do you need? How do you get the K for this front frame? Come on. You draw the deflected shape. You have to use a G top and a G bottom. You have to use the alignment chart. Our friend, the alignment chart. I'm going to go for about 3 minutes, and then I'm going to stop. And this is what I hope we can get of this last 3 minutes. I say, hey, what happens if we remove a brace? This system is still okay. It's still going to work. It's all good. But when it comes down to this frame right here, this frame, say, well, what's the K? What's the K? Well, the answer is somewhere between 1 and infinity. What's the answer? How do you figure it out? Well, we need our friend the alignment chart. What the alignment chart does is if we're really taking into account if IB, eye of the beam, is small, if it's like a noodle, like nothing with respect to the column, then our deflected shape is going to look something like this, and our K is going to be high, something like 20. Okay? K at 20 is crazy high. I mean, redesign high. Okay? K at 15, I've seen it work before, but oh my goodness. Okay? Okay. If I of B is small, if it is like a truss or big, beefy member, then we're gonna deflect shapes look something like this. I lied to you. I said between 1 and infinity. The answer should be 2 and infinity. But if I sub B is extremely large, our deflected shape is going to look something like that. You with me? Yeah. So how do we know? Well, we use our friend the alignment chart. If you've never used the alignment chart, get ready. I mean, this thing will tell you everything. Okay? It can predict the weather better than Gary England can. Okay? It can tell you which wine to order with your steak. Okay? I mean, it's going to predict that we're going to kick the crap out of Texas Tech this weekend. All right? This thing is amazing. Okay? Hope that doesn't come back to bite me. Okay, so that's what it does. It's just amazing. Okay? It can come back and you can turn all these beams and columns into, boom, a spring. You can turn all these beams and columns on the bottom, boom, into a spring. And as we call it, the Jackson-Moreland alignment chart. Remember, it's these two guys from Boston in World War I, or right before World War I, that derived it. They got tired of solving differential equations. I'm tired and I haven't done one in years. Okay? They got tired of doing them all the time. Alright? And so they made some assumptions. They made 5 assumptions. Got to start somewhere. They made 5 assumptions about the differential equation, and it went from solving a differential equation every time to, if I can do this for the top and do this for the bottom, then I can use this chart, and with the stroke of a pen, I can solve a 5-page differential equation. We all should send checks to their great-great-grandchildren, okay? Because they have really made our lives easier. Thank you, Jackson and Moreland. That'll be it for today.